everybody, welcome back. In this video, what I'm going to do is discuss a cool phenomenon called quantum tunneling, which is characteristic of the wave-like nature of matter. And we can actually engineer with this phenomenon. It's really cool what happens. It's even cooler that we can engineer and make things that utilize quantum tunneling. So the way I'll introduce this is, if you recall when we were talking about in the previous video, the one-dimensional infinite square well, we considered an electron trapped in some material, right? And we said we could approximate that with that infinite potential energy well. And then at the end of that video, I said, well, in reality, it'd be better to model it as a finite square well, right? Where the electron would actually have a chance to escape. So I want to pick up on that to explain how tunneling can occur. So imagine that we have 3 layers first. So suppose we have, similar to what we talked about last time, but I'm going to use 3 different materials instead of 2. So suppose we have 3 layers stacked like this, okay? And I'll call that x equals 0, x equals L, and the electron is trapped in the middle layer. If we were to sketch the potential energy for the electron, we might do something like this. So here's 0, here's L. And I'll do this in red. I'm going to still approximate that the electron is free to move in a particular layer. So that means that its potential energy is going to be a constant. Okay, so the value of the constant for one layer isn't really important. What's important is the relative size of the potential energy. So for instance, I could assign the potential energy to be 0 in the middle material. And then maybe it's at some value, because of the different makeup of that material, the potential energy is there to the left of 0, and this comes down. And then maybe there's a different material, so it is this value, okay, like that. So those represent the potential energies of the 3 different materials. Now, if the electron is trapped in that middle material, then maybe one of the allowed energies is that. Okay, so there's my E. And the electron, we would say, is just bouncing back and forth as it moves, trapped in that material. Okay, now remember that the total energy is the sum of the kinetic plus the potential energy. Okay, now, is there any way that you can get the electron to escape from that layer, or in terms of the picture, escape from this energy well? Well, yeah, somehow, if you excite this electron, give it some energy, maybe electrically, if you can get its total energy, give it some extra kinetic energy so that its total energy is up here now, well then you can see that it could actually go to the right and get out of the well. The difference, remember, between the total energy and the red potential energy is kinetic energy. So as it goes to the right, when it enters that right layer, that rightmost layer, it's going to have this much kinetic energy, and it can keep going, so it can escape from the well. Okay? Well, what you can do is you can engineer with another layer where you seem to violate classical physics. So imagine we do something like this. So we have the original layer here. This layer is the same, 0 to L. But what we're going to do is we're going to come in and we're going to put a really thin layer of a different material. Let's say that that's x equals m, and then we'll put that sandwich layer. So the electron is starting out here, but we have this thin layer right here. So if I update my energy plot, it'll look something like this, let's say. So this is 0, this is L, this is M. So now, by the right choice of materials, I could have, there is my leftmost material, then I'll say the potential energy comes down to 0 right here, right? And here we know that this is going to be like at this value. But suppose that by the right choice of this thin layer between 0 and L, that the potential energy jumps up. So maybe it's something like this. And then it comes down. Okay? Okay. Well, now, watch this. So suppose that the total energy of the electron, right, is up here. So you give it some energy, right? Now, if you do just a classical analysis, it looks like that electron is trapped, right? It can't get out of the energy well. Classically, kinetic energy cannot be negative, right? So I can't have the total energy being less than the potential energy. Okay, it's just impossible. So there's no way that the electron can go to the left or to the right. But an amazing thing. Now look, well, before we say the amazing thing, if I gave it this much energy, yes, then it could escape either to the right or to the left, right? But suppose it's down here with this energy. Well, an amazing thing can happen. If this layer between L and M is not real thick, relatively thin, relative to the wavelength of the electron, the matter wavelength, and the barrier is not too high, there is a probability that this electron can actually appear over here, even though classically it should not. Right? There's no way that the electron with that total energy should be able to go through this energy barrier, as it's sometimes called, and appear over here. But there is a probability, and you can actually calculate it. It's called the tunneling probability. Okay? And this is solely because the electron is acting as a wave. In terms of a wave, if you come up here, where we say the electron is trapped, right? As a wave, there actually is some penetration into this layer and into this layer. But because these layers are thick enough, the wave does penetrate a little bit, but it will reflect back. So it will penetrate a little bit, but then the energy will reflect back. Okay, so that's what's going on if you treat it as a wave. Here, same thing. The electron wave is actually penetrating to the left a little bit. But because that layer is so thick, it will all reflect. It penetrates a little bit into the barrier. But if the barrier is thin enough, before it has a chance to totally reflect back to the left, the wave will actually continue to the right. It tunnels through that energy barrier. Okay, and we can actually engineer with this. There's a device called a tunneling diode, which operates like a diode, but the current that goes through the diode is actually from tunneling electrons. And you can control it very, very, very well because that tunneling probability, that tunneling current, is very sensitive to the height of this energy barrier and the thickness of that layer. Okay, now, this sounds really weird, but you know what? This happens with waves. With light waves, it happens. So there is an analog, a classical analog with light waves to quantum tunneling, and this is known as frustrated, it's a cool name, total internal reflection. You guys remember TIR? Internal reflection. So what happens in TIR? Well, what we said is, right, if you have an interface between two materials of refractive index N1, N2, if N1 is greater than N2, we said that there is a chance that all the light energy will reflect. The condition is that this angle, this theta 1, has to be bigger than the so-called critical angle. Remember we said that? Then all the energy reflects, none of it is transmitted. All right, well, if you take a closer look at what's happening, there is actually propagation of energy into that second medium. But as long as that second medium is thick enough, and it doesn't have to be very thick, that energy will come back out. So that energy will get all totally reflected. However, what you can do is, if you make this layer right here, you add a layer that's thin enough, so you come in, even though you're coming in greater than the critical angle, and it's predicted that all of the light energy should reflect, if this layer right here is thin enough, the wave penetrates, and before all that energy can reflect back up into the first material, you will get some propagation into this third layer here. That's called frustrated total internal reflection, and it can occur. Now again, this layer has to be really, really, really thin, okay, in order for you to see this. But let me show you guys, and I'm just going to do a Google search, the easiest thing to do, and I did one right here on frustrated total internal reflection, and I want to draw your attention to these pictures over here. Okay, so what you see is these are two plastic prisms, okay, and there's an air gap. You can see that air gap right there. Now, this air gap right now is thick enough that you're seeing total internal reflection. See, the light's coming in like this, hitting this diagonal interface. That incoming angle is greater than the critical angle, so all the light energy is reflecting. You're not seeing any propagate into this second prism. But if you make this gap thin enough, see how they made this air gap thin enough right here? You're coming in with the same angle of incidence. A lot of the light is internally reflecting, but look, you see? You can see a little bit of light energy actually getting through that air gap, even though Snell's law says, no, all of the light energy should reflect. That is the optical analog of quantum mechanical tunneling. The weird thing is, it's particles that are doing this tunneling, right? In the quantum tunneling, behaving as waves. So, and you'll actually observe an electron in that right-hand layer when, if you just look at the energy, there's no way you should see that electron. Okay, so there's a probability that it will just tunnel through that layer. Okay, all right. Just to wrap up this diagram, this is cool. What they did then is, see that air gap layer? They actually filled it with a fluid that has the same index as the prisms. So now it's like there's no interface at all and the light goes straight through. That's pretty cool too. But this middle picture shows the frustrated total internal reflection. Okay, so one application of this is a tunneling diode, where the tunneling current is formed by electrons that are tunneling through an energy barrier. Another nice application of quantum tunneling, one that I wanted to mention, is a scanning tunneling microscope. I don't know if you guys have heard of a scanning tunneling microscope. So you may have heard of a scanning electron microscope. That's an older technology, and that's known as an SEM. That just bounces electrons off of specimens. The specimens have to be conducting, they have to be metallized. But what you're doing is you're bouncing electrons off the specimens and then focusing the reflected electrons to form an image. And you can get really big magnifications. I'm sure if you go on the internet, just look up scanning electron microscope images. You'll see images of flies and flies' eyes and things like that. So that's an older technology. But a scanning tunneling microscope, STM, this has been around maybe 20, 30 years, about 30 years. So this is scanning tunneling microscope. And what they do is, I'll draw a really bad picture of this, but you can actually image individual atoms with this. Now they just appear, they're still computer generated, right, images, but they appear as sort of like little spheres, okay, or like egg carton things. But the idea is that this all relies on an extremely sharp tip. So you have this tip, and at the tip right here, it's basically one or two atoms, the point. Okay, so here's this tip, and what you're doing is you're scanning the tip across some surface. Now, if I magnify this, if I blow this up, your tip is like this, right? It's comprised of some atoms. So I'm just going to stack them up like pool balls, but that's your tip. And then you have atoms here that make up your surface, right? And they're going to be separated by some distance. Here's the idea. There's a voltage difference between the atoms, right, of the tip and the atoms that make up your surface. Okay, now, if you just look at that voltage difference, it's not enough to force electrons to jump from the tip to the surface, but some will tunnel. There will be a probability that an electron will tunnel across that energy gap and actually make its way to the surface. So between the tip and the surface, there is a tunneling current. So there's a current that's produced by these tunneling electrons. Now, the size of that current is very sensitive to how close is the tip to these atoms, right? Because that's going to vary. The analogy is it varies the thickness of that layer up here between L and M. So that affects the tunneling current. So in one mode, what you do is you move the tip to maintain a constant current. So when the tip comes near an atom, it will have to go up a little bit. But when it comes to the region between atoms, it'll have to go down a little bit. So what you monitor is you actually monitor the deflections of the tip as it scans this surface. And by plotting those deflections versus spatial coordinates, you can actually image where the atoms are and where they're not in these surfaces. And I can show you some images. I don't want to talk for too long. You can look at these too. But if you just, I'm just going to Google STM images. And here are some. These are really cool. So you can just click on one of these. That's showing you gold atoms. Okay. This is blown up. So, and again, it's color enhanced by the computer, but you can actually see the crystal structure of where these gold atoms are. Okay, and you can see the resolution. This bar right here, that's 1 nanometer. Okay, so the resolution is quite remarkable, right? That's 1 nanometer, which is 10 angstroms. It's remarkable, and you can look at other images also. Here's one. Okay, you see right there, and oh, let me show you. IBM was one of the first, I think maybe the first company that actually did this. STM IBM images. They discovered that with this tip, you can also move atoms around on a surface. You can actually, now the atoms have to be able to move pretty easily, so they have to be the right type of atoms on the right type of surface. But what they were able to do was actually move atoms to spell out different things, like IBM. You can see right there. Another cool thing that they were able to do was to move atoms. Let me show you. In this picture, they're moving atoms around, you can see right here, to make what's called a quantum corral. So they were able to move atoms around on a surface to make this corral. And then they scanned it with the STM. And you see these ripples right here? You see these ripples in the corral right here? Make that bigger so you can see it. Those ripples are actually electron waves. Those are electrons that are forming standing waves, very similar to water ripples in a pond. But the electrons, they're trapped in this atomic corral. Certain electrons are that can move pretty easily on on the surface of the substrate, and they're reflecting back and forth. They're acting as waves, and you can actually see the electron matter wave ripples from the scanning tunneling microscope image. I mean, this stuff is so cool, I think, this nano world. And this is direct evidence that particles are acting as waves. I mean, I could talk more and more and more. I don't want to waste a lot of your time, but it's really cool if you start looking at some STM pictures. There's another related imaging technology called atomic force microscopy, AFM. Now, that doesn't rely on a tunneling current, but it's also another way that you can image individual atoms, AFM. In fact, AFM, an advantage of AFM is that you don't have to have conducting surfaces because it doesn't rely on a current. You can have non-conducting surfaces. And it relies on a little lever, and it's sensitive to the force between the atoms on the probe at the end of the lever and the atoms that make up the surface. But you can look up and read about atomic force microscopy also. Okay, so there's scanning tunneling microscopy, a neat application of quantum mechanical tunneling. And I'm going to stop, and next video we'll talk about, go back and talk about atomic physics. All right, bye-bye.